Good morning, everyone. I guess it's time to get started. So welcome. Thanks everyone for coming. My name is Michelle, and this is Jan. We are both SIG storage contributors and are here today to talk about our firsthand experiences with fixing a major security vulnerability in Kubernetes. We'll take you through the whole process, from when the issue was first reported to when the fix was publicly released. Along the way, we will deep dive into the technical details of the vulnerability and the fix, suggest some best practices that you can follow in your Kubernetes clusters, and also give a sneak peek at future directions we're exploring in Kubernetes to make it more secure. So first, how did we become aware of this issue? Well, in late November of 2017, a Kubernetes issue was opened with the title, Pod Security Policy Can Be Sidestepped with Innocent Empty Dir and Subpath. The issue then goes on to describe the exploit in full detail with the pod examples and output. I want to emphasize here that this is not the proper channel to report security issues in Kubernetes. GitHub issues are public and don't allow time for us to privately develop and release a fix before others can start exploiting the vulnerability. Luckily for us, a member of the Kubernetes product security team quickly spotted the issue and cleared out all the details. So, if you ever think you have found a security issue in Kubernetes, please follow our documented process on kubernetes.io. It starts with sending an email to security@kubernetes.io with the details of the issue, and a member of the product security team will evaluate the impact, respond back to you, and then coordinate the development of the fix and its release. So now I'm going to go into the technical details of this particular vulnerability that we worked on. To understand the vulnerability, some basic background knowledge on volumes is needed. So to illustrate this, I have an example pod spec here, and this pod is using a volume. When this pod gets scheduled to a node, one of the first steps is to set up and mount all the volumes that the pod uses onto the host system. And in this case, this pod is using an empty dir volume, which is just scratch space on the local file system. So as part of the empty dir setup, what we do is we create a directory on the host file system underneath the pod volumes root path as shown here. And once all the volumes have been set up and mounted on the host system, then it's time to start the containers. To start the container, kubelet needs to tell the container runtime. In this case, it could be Docker. It needs to tell Docker where on the host file system this volume is located at, and where in the container it should be mounted to. You can also see in this pod spec that there is a subpath of data 1 specified. What this subpath lets you do is, instead of mounting the root directory of the volume into the container, it lets you mount a subdirectory of the volume into the container. And to handle this, what we do in Kubernetes is, instead of telling Docker the root directory of the volume, we append the subpath to that root directory and give that combined path to Docker. So if we take this specific example, we'll take the root directory of the volume from before, append the subpath of data 1 to it, give this entire path to Docker. And then Docker will go ahead, take that path, and bind mount it into the container at the container's mount path of /mount/data. So Can anyone take a guess as to where the vulnerability might be?
There's somebody.
Anyone? What about the subpath?
Before the subpath.
Okay, if you put a dot before the subpath. We thought about that, so I think you can't actually specify dots in the subpath.
Those are safe.
Symbolic link, great. Yes, someone paid attention to the title of this talk. Great. So if you pay careful attention here, you'll notice that this data1, which is specified in the subpath, is a file that's created by the user inside their volume. And because it's created by the user, that means this file can be anything, including a symlink. So if we pretend, let's say this symlink points to something on the root file system of the host, then when we end up giving this path to Docker, Docker will go and bind mount whatever that symlink points to into the container instead of your actual volume that you specified. So now Jan is going to go demonstrate exactly how you can create such a symlink.
Thanks. So I hope it's readable. I have Kubernetes 1.9.0 that is still vulnerable. And I have a pod that's just very innocent pod that has one empty volume called my volume, as on Michelle examples. And I have an init container that creates a symlink inside the volume. This symlink is called data1, and it points to the root of the container file system. When the init container is done, the symlink is created. I start a real container that doesn't do anything useful, but it uses the symlink as a subpath, and it mounts it into MNT data inside the container. So if I create the pod, the init container starts, it creates a symlink, and the real container starts. And if I look inside the container, I have the my volume there, and it contains what I created. It contains just the symlink to root of the container, and there is nothing wrong with the symlink. But the magic happens if I look at the subpath, data1. It contains root of some file system, but it's not the host. Host is much smaller, and this is, it's not the root of the container. And the subpath contains root of the host. So I can look around, and I can see, for example, Docker socket. So I can kill or start any containers on the node. And the whole node is compromised. I can do whatever. I can look at var lib kubelet pods. I don't run so many pods, but I can see all volumes mounted on the node. I can see all the secrets mounted on the node. If there is a database running with, I don't know, credit card numbers, I can see them. And all this is just because we don't check symlinks in Kubernetes. So if I look at the host, on the host, this my volume is tempfs mounted somewhere in var lib kubelet. And what kubelet does, it gives the subpath, it gives the data1 to Docker to mount inside the container, and Docker or any container runtime bind mounts this symlink to the container, but the symlink is evaluated on the host. So the host root file system gets exposed to the container. So how did they fix it? The issue was reported just before KubeCon in Austin last year. So in Austin, we gathered together and brainstormed some solutions. and I'm going to illustrate our thought process because it wasn't easy to fix this issue. The first and most obvious solution was to check symlinks before we give them to container runtime. So if user wants volume my volume and subpath data1, we compute the whole path of the volume that user wants. We resolve symlinks, and if we see that the symlink points somewhere outside of the volume, that means that the user is trying to cheat, we refuse such volume and we won't start the pod. If the subpath is not symlink at all, we resolve symlink instead. In that, we get the same path as the result. We can see the subpath points inside the volume, and it's safe to use, so we allow that. And if the subpath is symlink, but the symlink points inside the volume, we want to allow that too, because people already use that, and it's a pretty useful feature of Kubernetes. So we want to allow this use case. So when we evaluate this, we either allow or deny the pod and give the final destination of the symlink to container runtime. This is obviously wrong, because user can still modify the directories that we are checking. So if we check that whatever user wants to use as subpath is safe to use, it's inside the volume, after the check, user can remove, for example, in this case, directory C, and replace it with a symlink to a bad place, back to the host. And we give this A/B/C to container runtime, but at this time, C is a symlink to the host, and again, user can get access to some bad places we don't want them to use. So we were thinking we need to freeze the file system somehow while we are checking the symlinks and when we are giving the final destination to container runtime. On Windows, the situation is pretty straightforward because they have create file syscall, which not only creates file, but with the right parameters, it opens them, and it can open them exclusively, so they can't be replaced with symlinks. So on Windows, we just log each component of the path, we check it's not a symlink, and when everything is all right, it looks valid, and it's inside the volume, we give it to container runtime, and container runtime starts container. After the container runs, we unlock the path. That's easy. On Linux, we don't have such luxury. We can't freeze file system. Well, we can, but it would stop the application that's running and uses the file system, and we don't want to do that. So we were thinking how to make things safer, and the solution was to use bind mounts. If you don't know what a bind mount is, it takes piece of file system hierarchy, for example, a directory, and makes it available somewhere else. So in this example, we bind mount the volume and its subpath, my volume /A/B/C, that's the subpath that user wants to make available to his container, and we bind mount to a safe place that is outside of user's control. User can modify my volume and its content, but user can't modify this safe place. And benefit of this bind mount is that after the bind mount, this my volume ABC shows the same content like the safe place, but if user changes anything in ABC, for example, creates some bad symlinks, it doesn't influence the safe place. The safe place is still safe, and it still shows the original content of the volume. So another very naive and very wrong solution. We check the symlinks as before. We validate that the symlinks are pointing inside the volume, and user is not trying to cheat. We bind mount the final destination of any symlinks that user used to a safe place. In this case, it's something varlib kubelet pods, volume dash subpath, and something unique. And we give this safe place to container runtime instead of content of the volume. So this way, we have a safe way how to give subpath volumes to container runtime, but everything before the bind mount is still unsafe. While we are resolving symlinks, while we are checking the destination, user still can't modify content of his volume or her volume and do bad things there. For a long time, we didn't know how to fix it properly, but then somebody suggested a smart trick to open file descriptor of the subpath and bind file descriptors instead of directories or files. We start the same like before. We resolve the symlink. And what this gives us is that at some point in time, not so long ago, user wanted to use directory A/B/C as the subpath volume. It doesn't need to, the data one symlink can be now completely different, but at some point in the history, this was the volume that user wanted. And now the goal is to open the last component of the path, that means C, and get its file descriptor. We can't just do open ABC, because it would resolve all the symlinks in the path, and the user could replace already A or B or C with symlinks, but we must do it smarter. And we can open the last directory that's not under user's control, my volume. User can see content of the directory inside their pods, but they can't replace my volume itself with a symlink. And then we safely dive into A, into B, into C. We don't follow any symlinks. And we get safe file descriptor of the volume that user once wanted. That was once reachable as A/B/C. It doesn't need to be reachable as A/B/C now, because user can rename things and move them. But the point is, user can move them only inside the pod. They can't escape the container right now. So now we have the file descriptor of the thing that user wanted to use, and how do we bind mount file descriptors? That's not possible. You can bind mount files or directories, but not file descriptors. That doesn't make sense. But there's the trick. If you look at the proc file system of kubelet, proc is basically virtual file system that shows tunables and statistics of all processes on Linux. There is a virtual directory called fd that contains all the open file descriptors. And if you look at item name 13, it's a symlink to the location of the file that's open. And the symlink is not tied to the path, it's tied to inode. So whenever a user moves A or B or C inside the container, the symlink follows to the new destination. And we bind mount this magic symlink instead of ABC directly. And what kernel does, it atomically resolves the symlink. It chooses the right destination of the symlink and bind mounts it to safe place. So that's the whole trick. We clean things up, and we give the safe place to container runtime. Short recapitulation. We didn't follow any symlinks while we are opening the file descriptor of the subpath that user wanted to use. And we can be sure that user could not escape the container by moving parts of the file system hierarchy inside the container, because he can move things only inside the container. And then we gave the final subpath to the container runtime safely. It took us quite a long time to implement this solution. This was just the high-level idea. There were many hurdles to climb, write end-to-end tests, fix the issue also on Windows, and so on. And how could we do that actually in secret in Kubernetes? If we develop the fix in Kubernetes/Kubernetes repository, we could create PR there and develop the fix there, but the development would be open, and somebody smart could see, hey, this is security related, I can misuse it. So there is a Kubernetes/Kubernetes-security repository on GitHub. You can look at it, and you won't find anything there. You get 4 or 4. It's private. Only the product security team can access it, and they give access to the repository only to selected people who need to fix security issues. So in this case, it was me, it was Michelle, and Andy from Microsoft. Nobody else could know about the issue. And we immediately lost access to the repository when the fix was released. I don't have access there. I don't know what security issues are being fixed there now. I have no clue. But the rest in the repository is the same like in Kubernetes. So you create pull requests, you can comment on them, you get the CI that you are used to. The only difference to me was that logs from the CI were in private buckets accessible only to Google employees. So I'm from Red Hat, and I'm in Europe. And if CI job failed, then I needed to wait for Michelle to wake up and tell me what's wrong. And we needed to be careful where we push things, because if we pushed our code to our public forks on GitHub, again, it would make the issue publicly available. And all the development is coordinated by product security team. So as a developer, I just follow orders, and I don't need to worry about the security aspect of the thing. I have a safe place to develop the issue and do some tests. When we had the fix, it was time to start thinking about releasing it. And again, it was coordinated by product security team. Me as a developer, I just follow orders. And the product security team talked to all the branch managers when it's a good time to release the fix. And also the security issue could be announced to private distributors list, which is a list of third-party Kubernetes distributors. These distributors and vendors, they get the fix and the issue before it's publicly released under embargo, so they can prepare the fix, they can patch their products, and they can publish the fix after the embargo is lifted. So all their products are safe when the issue is public. So the public disclosure happened 4 months after the initial discovery on GitHub. So it took us 4 months to prepare everything. Again, this was coordinated by product security team, and all the Kubernetes versions that were supported were patched and released within 1 hour after the disclosure. When this was done, then all the people who were involved in the security fix, that means developers, testers, release team, product security, they met together and created post-mortem document. This post-mortem is public. You can read it, and it contains like what went wrong, what went right, what can we improve in the future. Yeah, and that's about it. Like at this point, we lost our access to security repository, so we don't know. I can't even check the history of the pull request. And I'm handing over back to Michelle, who will tell you something about how to protect yourself from this issue if something like that is found in the future.
Thanks, Jan. So now I'm going to shift gears and talk about some best practices that you can follow in your own Kubernetes clusters. First, I recommend that you don't run your containers as the root user whenever possible. For this particular vulnerability, if a container was exploited and got access to the host file system, then the damage it could have done would be limited to only those files that the user has permissions to access. So you can enforce this by creating a pod security policy to require your pods run as non-root users. And you can also restrict the UID range that your containers can run as. There is a caveat in that your containers will still run with the root group ID. So if your container was exploited, then it could still access files that gave permission to that root group. This is being addressed in Kubernetes 1.10 with the Run as Group Alpha feature, which lets you specify what group you want your containers to run as. I also recommend that you use pod security policy to restrict the types of volumes that your containers are allowed to use. Now, for this particular issue, it might not have been very practical because you would have had to blacklist almost every single volume type except for the integer volumes. But nevertheless, I still recommend you try to restrict them whenever possible, especially when using host path volumes. If you still have to use host path volumes, then you should at least set both the allowed host path prefixes and the read-only setting. It's very important to note that the allowed host path prefix setting in pod security policy is only effective if you also require that your containers mount them as read-only as well. So now I'm going to talk about some future directions that we're currently exploring in Kubernetes to using sandboxed containers. This is using technologies such as gvisor and Kata containers with the aim to prevent this entire class of vulnerabilities from happening again in the future. Some of this work is based off of a core principle that we follow at Google, which is that any untrusted code must be protected by at least 2 security boundaries. The basic idea here is that if any one of the layers, security layers, gets compromised, then there are still other layers that can provide isolation. So how can we apply this principle to protect us from the subpath vulnerability? Going back, the exploit involved making the host system follow symlinks that were created by the user. So if instead we have a sandboxed environment that can provide our additional security boundary, and we moved that processing of the untrusted subpaths into the sandbox, then any symlinks that we would end up resolving could only resolve to paths contained inside that sandbox, preventing access to the host file system. So this is an idea that we are currently investigating today. So this doesn't exist yet in Kubernetes, but expect to see some movement over the next year or so. All right, so that is our full story. I know that was a lot of information that we packed into here. So to summarize the key points, first, if you ever think you found a security issue in Kubernetes, please responsibly disclose the issue by following our documented process. Next, be extra cautious when handling untrusted paths in your own programs. We detailed today 2 common vulnerabilities, a symlink race and a time of check to time of use race. And lastly, set restrictive policies in your Kubernetes clusters by default and design your applications to provide multiple security boundaries. Vulnerabilities are bound to happen, so the best mitigations you can take are to have multiple layers of defense. I also want to give a special thanks to Maxim Ivanov, who initially reported the issue to us and worked with us to make Kubernetes more secure. So if anything we talked about today interests you, please check out these links. First is the link to the product security team, which coordinates and handles all the security issues in Kubernetes. They are looking for new members, so you can check out their page on the process on how to join. Second is the Secure Container Isolation Project. This is the project that is looking into providing sandbox environments. And there's actually a talk later today in this very room on this project. So if you're interested in this topic at all, you want to learn about all the new secure runtimes, then please check that out. And with that, we can open it up for questions.
Yeah?
Hi, yeah. I'm wondering, how did you decide when to make the code public? Like you said that you checked it into sort of a private area. Is there like a process for making those security pieces of the code public? Or do you have to keep them private forever? Or how does that work?
Okay, so the question was, how did we actually decide when to make the fix public?
Well, when we had the fix, the product security team has some rules when a security issue can be made public, can be published. Like never disclose any issues on Fridays. And yeah, they just took a random date when all the branch managers had, I don't want to say they had time all the day, but there was no release in the process. And there was enough time to let the Kubernetes vendors know before the issue is published so they can fix their issue. All these details are on the product security team page. There is a process they follow when they release things, and you can find all the details there.
Mm-hmm. In general, though, I think it's a best practice to try to fix vulnerabilities as soon as possible so that you reduce the chance of someone actually finding it and exploiting it in the wild.
Oh, it's quite small.
Yes?
So you mentioned that it took about 4 months to release the whole thing. I wanted to know how much time did you spend in testing and development and how much was the rest of the process?
Okay, the question was, so we said it took about 4 months to develop the fix. How much time was spent actually developing and testing the fix versus the release process? I would probably say like 3.5 months were spent fixing and testing the fix. We went through probably 4 or 5 different iterations of the fix until we arrived at one that we were confident that would actually patch the issue. Oh yeah, and this was also, it was initially disclosed over like Thanksgiving-ish or after Thanksgiving, so, and then like a bunch of people went on to Christmas break like for half a month, so yeah, it kind of, yep. Yes?
So we just went through another CVE, and I'm sure it won't be the last. You mentioned you went through a bit of a learning experience with the development and testing process from a CI perspective. Do you feel like it ended up where you wanted, or would there be things you would want to see improved as we expect more of these to happen?
Okay, so the question was like, our initial, we learned a lot of things from the initial, the whole CI process and everything, and is there anything we would like to see improved? I know Jan definitely wants access to the private logs.
I want the logs. But that's basically all. Everything else was super.
Yeah, I think this was one of the first vulnerabilities where we really tested the CI infrastructure for this private repo. So I think actually the first like 2 months of it was the test infra team trying to like get everything, the CI to work. But definitely in the post-mortem document, which is public, there's a whole list of action items and stuff on how to improve the process. So you can check that out if you're interested.
I think we are over time.
Okay.
So you can find us.
Yeah, we'll probably off to the side or something if you want to ask more questions. Thank you.
Thanks.